So, hello everyone, I'm Isidora, and I will be telling you today about this project that I enjoyed a lot, and I worked on with Nastya, Daniel, and Anton. And here we were constructing an invariant to identify magnetic obstructed. Oh, am I sharing screen now? Great. Let's start again. Now you can see my screen, right? Okay. Yeah. So we were constructing a topological invariant for magnetic obstructed insulators. And well, before starting, I want to say that you can interrupt me anytime. You can unmute yourselves or raise your hand. So to start, I would like you to think about Hamiltonians. So in physics, we have Hamiltonians. These are objects that are continuous in some parameters, and we use them to describe different systems. Hamiltonians can have symmetries, and we can infer a lot of things from them. For example, if the symmetries are continuous, we can use Noether's theorem and find a conserved quantity. If the symmetries are discrete, then we can find other kinds of conserved quantities, like topological invariants. And one minimal example to seeing this is the SSA chain. So I will briefly introduce how to use symmetries to identify the topology in them. So here I'm showing two chains where the unit cell is this rectangle, and each cell has two circles. These are two different sides. So we have two sides per unit cell, and we can couple them in different ways. So for example, we can couple the sides between a unit cell or between different unit cells. And depending on how we use this coupling, we will have wave functions localized at the bonds. So for example, in the upper situation, we'll have the wave functions localized at the center of the unit cell where the bond is. And in the second one, we'll have the wave functions localized in between different unit cells. This is because of the dimerization. And we have only one wave function because each unit cell has two sides, and we use a condition of path filling. So with this, we're great. We can distinguish two different situations, and we can tell that the first one is different from the second one. However, we could also change a bit the parameters in our Hamiltonian by introducing extra hoppings, the ones that I'm showing here in gray. And if we do this, the wave functions will move. So they will move a little bit to the right or a little bit to the left, but these two situations will stop being distinguishable, because by tuning the parameters, we will be able to move from one case to another. And so in order to have them clearly distinguishable, what we have to do is to add a symmetry. And here, the symmetry that I'm considering is mirror one, so inversion, such that we fix a vertical axis here at the center of the unit cell, and we make sure that the left side is the mirror image of the right side. And so if we impose this restriction, we will see that the wave functions can only be sitting at the center of the unit cell or at the edge, because these are the only two symmetry invariant positions in real space. And so by using mirror symmetry, now we cannot move the wave functions to the right or to the left, even if we change the parameters of the Hamiltonian. So with this, we have two clearly distinguishable chains in real space. But the question is whether this is enough for topology. And to answer that question, what we have to do is to look at momentum space. So here I'm showing the one-dimensional Brillouin zone of a one-dimensional chain. And I'm showing you here two relevant momenta. These are 0 and pi, and the respective occupied eigenvectors of the Hamiltonian at these momenta. So what we see is that in the upper case, when the wave functions are at the center, the eigenvectors have the shape of -1, 1. And then at pi, they have the same shape. In the second case, however, when the wave functions are localizing between unit cells, we see that the wave function changes from 0 to pi. And so only by looking at these two momenta, we can tell that one case corresponds to the upper chain and the other corresponds to the lower chain. So only by using pi, we're good. We can tell that the two are distinguishable. And a more formal way to see it is to consider that these wave functions are eigenvectors of the symmetry operator, because these are symmetry invariant momenta. And mirror operates on these eigenvectors, and these are also eigenvectors of the symmetry, because when these momenta are invariant under mirror, then the eigenvectors of the Hamiltonian are also eigenvectors of the symmetry. So by looking at the eigenvalues, we can tell whether we're in the trivial case, which is the upper chain, or the mirror obstructed one. So only by looking at the symmetry eigenvalues, we can tell what phase we're in. And so this is a minimal way of telling the different topological phases that there are in a symmetry class. But this is only a summary of what happens in the Brillouin zone. So a different alternative would be to consider the one-dimensional Brillouin zone from -π to π, and to calculate the Berry phase. And in that case, we would have 0 or π, one associated with the plus eigenvalue of mirror, and the other one with the -1 eigenvalue. Does anybody have a question? No questions? Okay, then this is the introduction, because this one is a well-known situation. But the more interesting question is how to distinguish crystalline insulators in general. And in our project, we focused on magnetic insulators. And in particular, we focused in the symmetry class of C4T. So we're studying C4T invariant Hamiltonians, and we can use a similar approach. So we can consider a Hamiltonian with 4 bands, which are spinful because we have spinful time reversal symmetry. We consider a half-filling condition, and we take into account how the symmetry acts on the different spins. So 4-fold rotation rotates the spin by 90 degrees, in rough words. Time reversal symmetry flips the spin. And so what we find is the first atomic limit, so the first C4T invariant spin configuration, where we have a singlet at the center of the unit cell. So this square here is a unit cell, the circles are the atoms, and we see that if we apply C4T on a red spin, we will get the blue one, and if we apply C4T on the blue one, we will get the red one. And so this one is a C4T invariant configuration, just like we saw before with the SSH chain. We can keep looking for more atomic limits, and we find the next one, which is just like the previous one, but displaced by half a unit cell in the diagonal direction, where the singlets are located at the corner of the unit cell. So here we see that if we apply C4T on a red spin, it gets flipped to a blue one, and then it gets rotated here. But these two positions are separated by a lattice vector. And so by applying C4T, we get the exact same atomic limit, or an equivalent version. So by following this procedure, we get a third atomic limit, and that is where the spins are located in between unit cells. So we have a blue spin here pointing down in between 2 atoms. If we apply C4T, we get the red one, and if we apply C4T on the blue one, on the red one, we get the blue one. So this one is also C4T invariant, and we also find one displaced by a fractional lattice vector combination. And so by looking for atomic limits, we find 4 different spin configurations. And these are all C4T invariant, just like in the SSH chain, but also they cannot be smoothly deformed into one another while preserving C4T. So the question is whether each of these obstructed atomic limits indicates a topologically different phase. And one approach is to look at the symmetry indicators. So to consider the C2 symmetry and apply it at the X point in the Brillouin zone, because the X point is C2 invariant. But what we see if we do this is that there's only 2 situations, either C2 diagnosis singlet faces or spin polarized ones. So even though it helps to separate these two situations, it does not help to differentiate between spin singlet faces and between spin polarized ones. So the goal of our project is to, if possible, distinguish these faces better and to figure out a way to do this systematically. Is there any questions? Are there any questions? No questions? Okay. So here I put a reference called Topology Invisible to Eigenvalues in Obstructed Atomic Insulators, where you can read more about these cases in which symmetry eigenvalues don't help differentiate. And the conjecture here is that if this is the case, then these different faces can be resolved by using a Berry phase. So naturally, what we do is to look in the whole Brillouin zone, not only at C2 invariant momenta. So the full Brillouin zone looks like this. We have the gamma point at the center of the Brillouin zone, the M point at the corner, this is pi pi, and the X point, this is pi 0, this is Kx and Ky. And what we saw before is that X is a C2 invariant momenta and M and gamma are invariant under C4T. Well, C2 is not enough to distinguish the four faces because I showed you that it only distinguishes singlets from spin polarized ones. So we need to look for more. We need to find a quantity that takes into account more than just the X point. And one option is to look at the full Brillouin zone, but actually we realize that that is not necessary. We can very well consider a fourth of it, because by considering this portion, we can apply C4T and recover the full Brillouin zone. So this triangle constitutes a more minimal amount of information. And now to construct the invariant, we use Stokes' theorem. So this is a common practice. If you haven't seen it before, one can use it to prove that the Chern number is a quantized number. And it comes from the Kane-Melle invariant. And we apply it here to a portion of the unit cell. So we have, of the Brillouin zone. So we apply it considering this path from gamma to M, M to X, X to M, and then back to gamma. So Stokes' theorem says that the contribution of the boundary has to be equal to the contribution of the area. So the first part here is the contribution of the area, and this one is the contribution of the boundary. So in theory, these should be equal. However, here we're talking about faces. This one here is the Berry connection. This is the curl of the Berry connection, and these integrals give faces. So this is only true modulo 2 pi. And now for simplicity, we will consider, instead of Berry faces, the Wilson line. The Wilson line is defined as the exponential of the integral of the Berry connection. So it's a way of rewriting these continuous integrals in a discrete way, such that we can develop the procedure further. So we can take Stokes' theorem over the irreducible Brillouin zone and rewrite it this way. And well, before we saw that we had 4 different atomic limits. We had 2 spin singlets and 2 spin polarized faces. But the expression here tells us that this difference must be 0 modulo 2 pi. So it only tells us that this difference has to be a multiple of 2 pi. And it doesn't allow us to distinguish 0 from 2 pi, 4 pi, 6 pi. And that is what we would like to do. We would like to get a result and to assign it to one of these spaces. So we need to get rid of the 2 pi ambiguity. But before I continue explaining, I would like to see if there are any questions. No. Okay, so one way of getting rid of that ambiguity is to split the path into 3 paths, because thanks to C4T, the path that goes from gamma to m, is a symmetry image of the one that goes from m to gamma. So we can take advantage of the symmetry in order to get rid of the 2 pi ambiguity. Then we also have a path that goes from m to m, and this one includes the x point. So I'm not going to cover this today, but one can see that this path contributes the same information as the symmetry indicator. So we would like to split this Wilson loop here that goes around the irreducible breakdown zone into these 3 lines. However, Wilson lines are not gauge independent. And I think this is the main issue in the construction, that if one simply splits the Wilson loop into 3 lines, then there's a gauge dependent expression, and that doesn't really make sense. So one way to solve the problem is to consider a theta operator. That is the one that you can see here. It takes the C4T symmetry and it subtracts the inverse of it, such that this operator works as a Kramer's, this operator works as an equivalent of time reversal symmetry in this case. So it protects Kramer's like pairs at gamma and m. This is a trick that we took from the first reference here. And what we can do with it is to consider the overlap matrix. That is the projection of the symmetry operator on the occupied states. And by making use of it, we can fix the Wilson lines such that they are gauge invariant and not gauge dependent anymore. So with that, we can replace the Wilson lines in the expression that we had before, and we can obtain an invariant that is well-defined modulo 4. So if anybody has questions about this procedure, I think this is the right time to ask. No questions, because I'm skipping a lot of steps. Well, an important point here is that by construction, our invariant is quantized, and it is also gauge invariant. So that's great. And well, I see that nobody has a question, but I have a question. So we have an invariant. It is quantized. It is gauge invariant. But does it actually work? Does it label the atomic limits that I showed you earlier? In order to answer this question, we have to have Hamiltonians that represent the diagrams that I showed. So the way we do that is by considering the following construction. So if we want to get spins that are at the center of the unit cell, we couple, we consider px and py orbitals, and we couple opposite spins within the same type, such that by coupling px within itself, we get a spin down here, and py within itself, we get a spin up here. Then to get the next atomic limit, for example, the other spin singlet, we can couple spin down and spin up, but from next neighboring unit cells, such that they localize in between diagonal unit cells. And then the same with the py orbitals. In the third case, when we have spin downs and spin up in between the unit cells and then not singlets anymore, we use a similar procedure. So we couple py orbitals within themselves and then px orbitals within themselves, such that the dimers localize where we want them to be. And by following this procedure, we can obtain the 4 atomic limits. And now to test the invariant, we should consider a general C4T model, or as general as possible. And we do that by weighing each atomic limit. So here, for example, this one we call H0, H1, H2, and H3, which is minus H1. And we weigh them with different coefficients, and we add terms that break any other symmetries that are not C4T, such that we obtain a Hamiltonian that can reproduce all atomic limits and that doesn't have any additional symmetries. So, well, after having the atomic limits, we can test the invariant. And this is what we find. We see here the phase diagram. I'm showing in the color bar the invariant in discrete values. It takes 0, 1, 2, 3. And in the x-axis, I'm showing a combination of the weights, such that, let me make it clear. So such that here we find the combination that has beta equals to 1. So that would be an atomic limit, the one that I'm showing here. This other case is where nu equals 0. So that is the trivial phase, where the spins are localized at the center. This one here is another atomic limit, nu equals 3, where there's a spins polarized this distribution of the spins in the unit cell. And in green, we see nu equals 2, which is the singlets at the corner of the unit cell. So the phase diagram shows that the invariant is quantized, and it only changes under gap closing conditions, which is something that we want. So the coloring in this plot has transparency that is proportional to the gap, or inversely proportional to the gap, such that the white represents gapless regions. So here I'm showing the case where lambdas are 0. So we have no extra symmetry breaking terms. But if we add them, we see that the phase diagram becomes more complex, but it still behaves according to what we expect. So the invariant is still quantized. It is still gauge invariant, and it labels all the atomic limits. Now, interestingly, not only we have transitions from 0 to 1, like the one here, that's a traditional, the standard case, through a phase transition, invariant changes by 1. And for example, also here from 1 to 2, but we have transitions from the red region to the green one. So these are phase transitions where the invariant changes by 2. So by looking at the Brillouin zone, we realize that the invariant changes by 1 when the gap closes at the x point. So these are all the transitions that the symmetry, the C2 symmetry can detect. But the transitions where the invariant changes by 2, so here from green to red, are overlooked by the C2 symmetry. So our approach is able to go beyond symmetry indicators and to diagnose the topological phases that appear in the C4T symmetry class. So as a summary, we identified the 4 obstructed atomic limits in this C4T symmetry class. We constructed a topological invariant. We also constructed the Hamiltonians to reproduce the different atomic limits and the general Hamiltonian, and we tested it, and it works. And I think the most relevant part of the approach is that our invariant detects beyond symmetry indicators, and it shows that without using the Pfaffian, one would not be able to classify these 4 phases. And so Berry phases alone are not detecting all the transitions, but the Pfaffian helps to find them all. Thank you. If you have any questions, I think this is the moment to ask.
I've got maybe one small question. In the slide before the phase diagram, you had that H3 is equal to minus one of the other ones. Can you explain why? Or why is it minus H1 and not?
This is minus because this configuration here is the time reversed image of oh, they're mislabeled. So sorry about that. So this one is the time reversed image of the one here. So these are let me maybe show a different one when they are. So these are these two configurations. So if we apply time reversal symmetry on this configuration of spins, we will get the one on the right because time reversal symmetry flips the spins. And so by constructing the Hamiltonian and applying time reversal symmetry, we realize that the Hamiltonian of this one is minus this one.
Okay, thank you.
Now, importantly, these two are not equivalent because we do not have time reversal symmetry, but only the combination between C4 and T. Are there any other questions?
I am wondering, is there any bulk boundary correspondence coming from these topological phases?
Yes, so that is also something we looked at. So as you probably know, so by looking at these at the construction, one can see how the bulk boundary correspondence will be. So, for example, in this atomic limit, if we only consider the number of unit cells that are shown here, we see that each unit cell has two states in it. So the trivial phase does not have any boundary modes. But for example, this one here has this uncoupled spin. So if we had another unit cell, this spin here would be coupled, but it is not. So we will have a corner mode in this case. And then something similar happens in these other two cases where this unit cell has three bonds. So we will have edge modes. And that will depend on the geometry because in a squared geometry, different number of unpaired spins will be localized at the corner or at the edge in each phase. So the bulk boundary correspondence is not as strong as in these strong phases because it depends on the geometry. And but we can see it by looking at the unpaired spins that there are at the boundary. Well, I think if there are no other questions, we can.
Maybe one more question.
Oh, yeah.
Is the invariant then dependent on the geometry of a square unit cell, or could it also work for like a honeycomb or something else?
The invariant doesn't depend on the shape of the unit cell. And the shape of the lattice, because it's a bulk quantity. So the Brillouin zone does not care about the terminations of the lattice. So it doesn't change.
Okay, thank you.
Mm-hmm. Well, if there are no more questions, I think we can conclude.